Welcome to the online course on finite element method. This course covers the fundamentals of finite element method. Student will be made capable of understanding the concepts of finite element method by giving very simple examples so that he can understand the concept properly. Next is the problems that are solved in finite element method will be understandable by with very good examples and how exactly you can um, adopt the same concept in software and any student who is feeling very difficulty in understanding the concept of finite element method, he can easily understand this concept through this lecture series. So I am trying to I'm trying to build this lecture series for students, engineering students, who are not able to understand the finite element methods concept properly or feeling it difficult to understand. So I will make it as simplified as possible so that you can understand it properly. Now, finite element method, getting into the fundamentals of that, before that, let us understand what is finite element method. To understand the concept of finite element method, you need to know three methods which are used for any particular analysis. When you do or when you want to solve any particular problem, you can solve the problem in three ways or in three methods. One is the experimental method, second one is the theoretical method or analytical method, and the third one is computational method. How exactly we can go through these methods, these three methods? To understand that, again, I will get into some a simple example. You take a cantilever beam. I know everybody are familiar with cantilever beam. Cantilever beam is a beam which is normally fixed at one end and free at the other end. And you have already gone through this in your strength of materials subject or probably the mechanics of material subjects in your lower semester. So at one end it is fixed and the other end which is free, that will be subjected to some load. If I take that load to be some newtons, and the other end is totally fixed in all the 6 degrees of freedom will be completely constrained. Now, if I want to know what is the bending stress in the problem or in the beam, how do I find it? I have three options, as I told. Three way of analyzing the problem. One is experimental method, second one is theoretical method, and the third one is computational method. Now, in experimentation, I can fabricate the given beam with the required dimensions and length or whatever the cross section is there. I need to fix it at one end. I need to apply a load on the other end. I'll connect the strain gauges to the beam. When the load is applied, strains will get developed, which are recorded by the strain gauges, and in the monitor it will be displayed. From the strains that I am getting, I'll be able to extract the stresses. That is one way. Correct. If you have done the same thing in your tensile testing machines, universal testing machine, tensile test you have done, you've taken a tensile specimen fixed at both the ends and try to pull it, try to analyze the strains, or deformation, whatever is. Same thing happens here also. Now, that is one way. That is the experimental method. Second method is analytical method, or you can also call it as theoretical method. How to deal with this type of method? Here, what you're doing is you're trying to get the solution through governing equations. Like, if I want to know what is the stress, bending stress in the beam, I'll take the governing equation sigma b is equal to moment by, or bending stress is equal to moment by section modulus. Correct? Moment is load into distance divided by section modulus is bd square by 6, where you get 6 into 6 into pl divided by bd square. So to understand the concept properly, let me take this. So here, if I take a beam, it is like this. The beam, cantilever beam is like this, which is of square cross section, suppose. Okay. So here, what you are doing is you are applying a load at one end, and it is fixed at the other end. Length, you have a certain length is there, say 1000 mm, 1000 mm. Here the cross section is 10 into 10 mm. Okay. Now, when you do experimentation, you apply strain gauges everywhere, somewhere over here, and try to record the strains. Correct. From the strain, you'll be able to extract the stresses. Now these are the strains. Correct. Now, in theoretical method, what you do, you take sigma b, bending stress, is equal to moment by section modulus z. That is, moment is load into length or distance divided by section modulus is bd square by 6. Correct. This is taken as 6 into p l divided by bd square. Now here, what you will do, you will take, so here sigma b by z, sigma b is equal to m by z is nothing but the governing equation. Now here load is 100 newtons. I will take load is 100 newtons. Okay, load is in 100 newtons. So 6 into 100 into length is 1000. Correct. Divided by 10 into 100. Correct. It means 10 into 10 square means 10 into 10 is 100. So here, what I'll do, I can directly cancel this and this. So you'll be able to get 600 Newton per millimeter square is a bending stress. This is the theoretical or analytical way of analyzing the problem, isn't it? So you'll be able to understand the concept from this. Now, is there any other way that you can do the analysis? That is the final thing. That is the computational method. Computational method, or you can also call it as numerical method. Okay, computational method. So, what is computational method? If you want to solve any particular problem by the support of software or computer, that is known as computational method. Any method that is, or any way of analyzing the given problem using computer, we normally call it as computational method. Sorry, this computational, ta, computational method. Okay, computational method. Now, computational method. So now computational method is the method where it uses the software to analyze a problem virtually. Means here, what I'm doing, I'm virtually creating the model of this cantilever beam. I'm virtually applying the boundary condition at one end, and I'm virtually applying the load at the other end, and I'm virtually analyzing the bending stress at the fixed end. So all these things which are done virtually using the software in the computer, that is known as computational method. So finite element method is one of the methods in computational method. Using that particular method, we can extract the bending stresses. Correct. So three ways of doing is experimentation means you're fabricating the cantilever beam. You're applying the boundary conditions in real. You're applying the loading conditions in real. And here, what you're trying to do is you're trying to extract the bending stress by using the strains that are getting generated. When you're dealing that with analytical methods, what you're doing is you're trying to get the governing equations like sigma v is equal to m by z, and then you're trying to extract the bending stress. Later, this is the computational method, which is one of the methods. Computational method is a branch in itself where you're trying to extract the results using computer virtually. So finite element method is one of the methods in computational method. Finite element method itself is not computational method. It is one of the methods in computational method. There are many methods in computational method, like finite volume method, Gauss elimination method, Newton-Raphson method. Many methods are there. So you will get book on computational methods, or you can also call it as numerical methods in engineering. You'll get a book on that. You can study the different methods that are available in computational methods or numerical methods. Now, finite element method is one of the computational methods which are used here. And using the finite element method, we can extract whatever the results that we are expecting. And um, the analytical procedure is also very simple in comparison with other two methods. Why I'll say, because what happens is there are certain limitations for the other two methods which are there, like experimentation method and um, this one. What is that? Analytical method. If you take experimentation method, I have taken a simple cantilever beam experiment I have done. If the if the problem is too complicated, then what happens? The cost that is required for um, fabricating the component, for generating the fixtures, and creating the experimental setup, it's very costly. You cannot afford. Sometimes you do want to do crash analysis of an aircraft, or you want to go ahead with the turbo engine design. So many things will be need to be addressed in that particular design. Not only a simple conditions, many conditions needs to be satisfied. So in order to satisfy that, the cost needed for doing the experimentation is very huge. So what you are trying to do is you are trying to do the analysis of these complicated experimentations numerically using computers. Why not I go for analytical method? Again, analytical methods are confined only for simpler geometries and simpler loading and boundary conditions. You cannot try the same thing using complicated boundary conditions, loading conditions, and complicated geometrical shapes as well. So these two methods, the experimental method and the analytical method, have limitations. But a finite element method has no restrictions. It can handle any type of geometrical complications. It can handle any type of loading and boundary condition complications, and it can give you the result. But the one thing that need to understand here is whatever the results that we get in experimental method and whatever the results that we get in theoretical method are more accurate in comparison with the finite element method result, because finite element method result has got some approximations. So we normally call finite element method to be an approximate method. Means, what do you mean by approximate method? Means if for the actual result or the exact result that is there for, suppose, 600 Newton per millimeter square is there for this particular problem that we have in front of us. This same problem, if I do it in experimental, I'll get 600 Newton per millimeter square. If I do it using analytical method, I'll get 600 Newton per millimeter square. But same thing, if I do it in finite element method, I may land up somewhere around 597 Newton per millimeter square, or suppose I may exceed it also, like 604 Newton per millimeter square. So it is not properly getting converged to the exact solution. So we normally call the finite element method as the approximate method. Finite element method as the approximate method. FM is called as the approximate method. It is because the simple funda here is the results that are generated in finite element method are not accurate. Okay, accurate means you. It doesn't mean that you cannot. You can directly you cannot take the result that is generated from finite element method. You need to take means the difference from the exact solution to the approximate result will be very very small, but that is affordable because when finite element method can handle complications in the problem, we can compromise on slight variations in the results. That is okay. So today's class, we have understood what is finite element method, how it is different from experimental methods and analytical methods. Okay, and in the coming classes, I will explain you how different and how to do the calculations in finite element method, basic calculations, steps involved in finite element method. All those things will be addressed in the coming classes. Okay, please subscribe to my channel and like the video. I'll be getting in touch with you people uh, with very good um, um, simplified way of understanding the engineering problems, not only for finite element method, for mechanics of materials, for design of machine elements, which are engineering subjects that you're finding it difficult. We'll try to get the simplified way of doing it. So next video, I'll get into more details into finite element method.